Let us consider the following problem. A charge Q is added to neutral metal ball of radius r. Find the pressure on the surface of the ball due to electrostatic forces between excess charges. First, we will discuss why this pressure exists at all. To be specific, we select the added charge as positive, and recollect that the charges on the conductor are located on the surface of the conductor. And because we have a symmetric sphere, we can conclude that the charges are evenly distributed on the surface of the ball. And then we select a small area on the surface of the ball. This area is equal delta A, and inside the area we have charge delta Q. This charge interacts with the charges outside this area, and this interaction is repulsive according to Coulomb law. And we estimate just qualitatively the magnitude of this interaction. If we take the charges on the opposite sides of the ball, and then the electric force on the charges inside this area points in opposite direction and is relatively small. And then if we select the charges on the sides of the ball, they generate larger forces which points in these directions. The charges close to this area create the force of greater magnitude, and these forces have such directions. The net force on this small area is the force which is normal to the surface of the conductor, and this force is due to excess charges outside area delta A. The existence of this force is a reason of appearing the pressure on the surface due to excess charges. From definition, pressure is the ratio of force over area. And now we replace, for simplicity, the magnitude of these forces using the concept of electric field. So if we consider electric field due to excess charges outside area delta A, then the force delta F is equal just a product E2 times delta Q. Now we consider the problem in more details. So we start with uniformly charged ball and calculate the surface density, which is defined as charge over area. For area of the ball, we have an equation, which you see here, A equal 4 pi r squared, and plugging in this value to equation for sigma, we get the following result for surface charge density. We also know that the electric field due to surface charges is normal to the surface, so in different points it points differently. And magnitude of this field is equal sigma divided over epsilon naught. Epsilon naught is permittivity of free space. Now we consider the same ball with the same surface charge and select small area and assume that the charge due to this area, only this area, generates the electric field which we denote E2. Without proof, we take that E2 is equal sigma over 2 epsilon 0. The proof of this equation will be given later. We assume that this area has surface delta A and charge delta Q. Delta Q can be represented as surface charge density times area of this part of the ball. Because of existence of E2 and charge, there is a force on this part of the ball, delta F, and delta F is equal product of electric field times charge. We will use this equation for electric field and this equation for charge to calculate delta F. We have the following equation, and this is electric field and this is delta Q. We open the bracket and we have more simple equation which we rewrite separately. We know that pressure is delta F over delta A, and from this equation we get immediately that pressure is equal just sigma squared over 2 epsilon naught. We plug in sigma from here and get the final answer in this form. So the pressure on the surface of the ball due to excess charges is given by this equation. Let's now estimate the magnitude of this pressure for following parameters. We take a radius of the ball 1 centimeter, charge equal 1.4 microcoulombs, and we know that the permittivity of free space is given by this number. We plug in all this stuff to equation for pressure, and we get a simple answer that the pressure is equal 70 kilopascals, or it's approximately 0.7 atmosphere. It's not a large pressure, but it is not a small pressure. It's almost atmospheric pressure. Now we return to the proof of equation for electric field E2, which was introduced previously. We start with consideration of the metal ball charged with positive charge Q. The charges on the conductor are distributed on the surface, and electric field points normal to the surface. In any textbook on electricity, you can find that electric field E on the surface of a conductor is given by this equation, where sigma is surface density and epsilon naught is permittivity of the free space. We select a small area on the surface of the ball, which can be considered as a planar, and charge on this area we denote as delta Q. Then we represent electric field E as a sum of two electric fields, E1 due to electric field generated by this charge on this area, and E2 which is due to excess charges outside of this area. And we start with calculation of the field E1. To find E1, we select Gaussian surface in the form of the cylinder, which includes charge delta Q and has the area delta A on the upper and bottom boundary. Electric field E1 due to this charge points here on the upper boundary and points in opposite direction in the lower boundary. Then we will use Gauss law, which states that epsilon naught times F, where F is the flux of electric field through this Gaussian surface, is equal delta Q, the charge inside Gaussian surface. The charge, as we know, is a sigma times delta A, and from the other point of view, flux is a product of electric field at the upper boundary and area of this boundary, plus product of electric field on the lower boundary and area of this boundary. So we have this equation for the flux. We plug in this equation to the previous one, cancel delta A, and we have for E1 the equation of such form. Now, to calculate E2, we find E2 from the equation for electric field E, and E2 equal E minus E1, and then use the magnitude of E and magnitude of E1. And we find immediately that E2 is sigma over 2 epsilon naught. This is exactly the value of this field which we used before. At this point, we have finished consideration of the problem.